We now look at application of integration. For this lesson, we will just look at the area between curves. Then later on, we'll talk of the volume of a solid of revolution. And after that, we also look at what we call the arc length. And then finally, we look at the area of the surface of revolution for our purposes. So when we are dealing with the area between curves, these are some of the basic things that you may take note of. Let me call it area between curves. And then the first thing that it's of importance is sometimes it's necessary to sketch the region between the graphs, say of F and G, on a given interval. Yeah, it's sometimes necessary. And then number two, after sketching, then it will help you to be able to draw what we call the representative rectangle. This rectangle will have the height, say f of x minus g of x, depending on the situation, and the width, delta x, such a way that when you look at the area of that representative rectangle, it's f of x minus g of x. Then if you check in your notes, we explained that we start with a single rectangular strip, we find its area, then we partition that region into an infinite number of rectangular strips, and then we allow the limit to approach infinity, and then we end up with the integral, which gives us the area under or between the two curves. So number three, after doing that, you must make an observation. You observe that the height of the rectangle f of x minus g of x is the integrand, then the width, delta x, reminds us to integrate with respect to, say, x or y in other cases. We will take an example. Where they say find the area between the graph of y equal to minus x squared plus 4 and y equal to 3x plus 4. So the first thing, of course, is to draw the graph and see how it looks like. These are simple parabolas. Sorry, this is a simple parabola. This is a simple straight line. The gradient here is positive, so the straight line will be like this. So in other words, if these are our axes like that, the straight line will go like this. And then the parabola, I've got a maximum at 4, must come down like that. But we are not interested in this section because it won't be between the two graphs. And so if we draw this again, both of them will be passing through 4. Maybe I can draw our parabola passing through 4 like that. And then we come to our straight line. Our straight line again must also pass, through 4. Oh, damn it. It didn't work very nicely, but anyway, we want our straight line to go like that. Okay, so it passes through 4. Then we now have to find this. This one is clear. So we can talk of points of intersection. When we speak of points of intersection, if we have two graphs, we understand that at the point of intersection, the two graphs will be equal. So we say minus x squared plus 4 must be equal to 3x plus 4. This tells us that minus x squared minus 3x is equal to 0. Minus x into x plus 3 is 0. X is 0, or x is minus 3, like that. So x is 0, it's up there, we are fine. X is minus 3, it's down here, minus 3. Then we can find the corresponding value of y. We substitute there. We have minus 9 plus 4, which is a 5, but it's not important to us. What is important is the value of x, because we want to integrate with respect to x. We are not going to change anything here. And then we can draw our representative rectangle just to indicate to us that it is going to touch both graphs at any given point, like that. And then it is telling us that we are integrating with respect to x there. Then it tells us now that the area is the integral. For simplicity, we can write from A to B, and then we talk of this graph and that one. This graph is y equal to minus x squared plus 4. This one is y equal to 3x plus 4. This one is on top, this one is the bottom. So we can say y on top, y at the bottom. So we will have y on top minus y at the bottom. Then with respect to x, like that. If we do that, this is going to be the integral. We are integrating from minus 3 to what? To 0. Y on top, it's a minus x squared plus 4. Y at the bottom, it's a 3x minus 4. And then all these are in terms of dx. So if we do that, this is going to give us the integral from minus 3 to 0. Simplify, we have minus x squared minus 3x dx, like that. And then this will be equal to integrate. We have got minus x3 over 3 minus 3x squared over 2. We're evaluating this from minus 3 to 0. Then we make our substitution, put 0 here, put 0 there, then this will be 0. Then we subtract, put minus 3 here, it will be 9. Put minus 3 here, it will be 27 over 2, like that. And then this will be minus into minus 9 over 2, which is 9 over 2, which is 4 whole numbers, 1 over 2 square units. Okay, let us throw this one away and take another example. Example number 2. Again, we want to find the area between x equal to y plus 2 and x equal to y squared, like that. So this is illustrating another kind of a situation. It's just an ordinary parabola like this. This is a straight line. Gradient is positive, whatever, and then it goes all the way, it cuts y here at -2. And then we are interested in finding the points of intersection. So point of intersection, again, it's a situation where y squared equal to y plus 2. So y squared minus y minus 2 will be 0. Y minus, just factorize, minus 2 into y plus 1 will be 0. So y it's a 2 or y it's a -1. So when y is a 2, x will be a 4. Y is a 2, x is a 4. Y is a 2, x is a 4. There we are. When y is -1, y it's x it's a 1. 1 minus 1, like that. Now we observe that it will be easier for us to draw our representative rectangle like that, where now this will give us change in y. In other words, we will be integrating with respect to y. So area is the integral from, say, C to D of x to the right minus x on the left dy, where we take this as x equal to y plus 2, this as x equal to y squared. So this is x on the left, this is x on the right, like that. So if we have done this, this will be equal to the integral from -1, because y it's running from -1 to 2, x on the right, it's y plus 2, x on the left, it's y squared, and then our dy. This is equal to, now if you work this out, you get y squared over 2 plus 2y minus y cube over 3 minus 1 to 2, like that. And then we do our, we evaluate, substitute 2 here, 2, 4 divided by 2. Okay, let me make it slow, but yeah, we put 2 here, it will be 4 divided by 2, it will be 2. Then plus, you put 2 here, it will be 4. Put 2 here, it will be 8 over 3. Then we are subtracting, we put 1, we have 1 over 2. Put 1 here, we've got -2. Put 1 here, we've got -1, which will be plus 1 over 3, like that. This will be equal to, then evaluate, simplify this. When you simplify, you'll get 9 over 2, which will be 4, 1 over 2, like that. And then finally, we just want to put a note for you, which you can use to solve a little bit more interesting problems. Say, note that for the area between, say, the graphs F and G, and between the lines, the vertical lines, x equal to A and x, say, equal to B, as given below, may be found as follows. We advise this. Say, for instance, you have that one, then you have maybe a blue graph. It's going like that. Then we have, let me use another color, a red graph. Yeah, going like that, say, for argument's sake. Then we have here our B. We have, say, our A. This is x equal to A. This is x equal to B. And we are interested in finding the area of the shaded region, like that, where, as we are indicating, this is y equal to f of x, and this is y equal to g of x. So what we are saying is that the total area of the shaded region is this one, these 2, 3, and 4. You add all of them. Now, the good way of finding them is simply saying that the area is the integral. You partition here, you check, oh, this is A, then this will be B, this will be C, this will be D, this will be, this one was not drawn very nicely, but we want this to be our E. It was not drawn nicely, but you can see what we want to talk about. So the area will be calculated from A to C, and then we check f of x is on top, then we subtract g of x, which is at the bottom, and then dx. We add, then we check C to D, which one is at the top, g of x. We subtract f of x, then dx. Then we add here, which one is at the bottom, that one, the integral from d to e dx. And finally, S4 is the integral from e to b. The one on top is g of x. Then you subtract the one at the bottom, and then dx. But one can use the absolute value, but you still have to partition A and B the way we partitioned it, like this. But the only thing that is that if you, instead of writing square brackets like this, you put the absolute value, it will no longer matter which one is on top, which one is at the bottom, because at the end we know that area is positive. So the area will be positive, 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 and then you are adding positive numbers. But if instead of putting the absolute value, you forget to put them in the proper places, you'll find that sometimes you have this which is a positive, and then you may produce a negative number, and so on. So it will mean that you will have a positive number, you subtract the negative number, then you should find a way of adding it back, and sometimes it's not easy to do that. So you can look at the other examples in the pamphlet and do the exercises. They will help you